So good afternoon everyone. So this is CSE 213 digital design with HDL hardware descriptive language. Today is August 10, 2024. So last time we talked about various things. So somebody can tell me what we studied last time. Okay, who is confident? Who, like, you have to tell everything, like what we studied, various topics, right? Number system is the chapter name. What we have studied in the chapter, right? Yeah, tell please. Yeah, so that one is this one, right? Correct me if I am making any mistake, right? And for negative side, after decimal, you are going to have -1 or -1, right? So this is what we studied. Then okay, decimal to any system, whichever base, like any base system. Binary to octal, binary to hex. Anything else we studied? We also studied this binary to decimal, or any system, any base system to decimal, right? We studied this. So any doubt in these topics? Right. Any doubt? Okay. No doubt, then we can go further, right? So what we studied is as follows. Like binary system, which has, let's assume that there are 12 bits and all are 1. It is expressed in terms of octal as all 7 with 4 bits, or in hexadecimal all F in 3 digits. So during communication between people about binary numbers in the computer, the octal or hexadecimal representation is more desirable because it is okay. This color is fine, right? Which color was problem? Okay. No color is problem, right? All color are visible, right? Okay. So most of the time, the computer manuals and everything is either written in octal or hexadecimal, because it gives output or the numbers in less number of bits, right? So that's the best part, and you can take the choice between them is arbitrary, although hexadecimal tends to win out since it can represent a byte with 2 digits. So that's the best thing about that. But still people are using octal also, people are using other system also. So depending on you as a hardware designer, so which one you want to use, accordingly you can do that, right? And that's why we studied octal and hex from binary system, right? Now let's go further. We studied something called binary addition, right? Addition is actually quite easy. Do you know how to, let's assume that A and B, 2 functions are there. I want to add them, right, using some digital logic gate. Do you know any digital logic gate which can add 2 numbers? Yeah. Or is not adding. Or can add? No. And can add? No. Let's look at that. If 0, 0, 0, 1, 1, 0 and 1, 1, 4 possibilities are there, right? If it is OR gate, by the way, I assume everybody knows all the gates. Okay. If you do not know, let's assume that you do not know, okay, I am going that way only. If it is OR gate is the one which is logical OR gate. Any one of them is 1, then output is 1. Okay. If any one of them is 1, then output is 1. So you look at here, this one is 1, this one is 1, this one is 1. However, in the case of this one, it's 0. Whereas in AND, what will the output here? 0. This one 0, and this one is 1. So what does it mean? If any one input is 0, output is 0, right? AND gate is actually denoted with center dot, right? And this one with plus, but it does not go that way, right? It does not add that way. It's OR, logical OR operation is there. So now the question remains there. Do you know any logic gate which is going to add two quantities? Yeah. Okay, let's try with NAND. So NAND is just opposite of this one. By the way, addition. Let's do the addition. Okay, addition. We are doing the addition. So 0 plus 0, 0, 0 plus 1, 1 plus 0, 1 plus 1, 0 with carry 1. As you have only one bit available in addition, so you can drop this out, right? But actually there is 1 is there, carry is there, but we are dropping it. It's not available because we do not have available bit, right? So that's why we are doing this. So this does not look alike to this one, not this one, not this one, right? So somebody gave one answer, XOR gate, right? So with this, right, circled one with addition. I am saying that, look, we have only one bit available. That's why it can represent either, like the actual addition of 1 1, 1 plus 1 is actually 1 0, but this is not available. We have only one bit is available, right? That's why we are saying that we can, like, we are dropping this. However, the actual answer is the total one, 1 0. 1 plus 1 is equal to 1 0, where this one 0 I am going to treat it as sum and this one as carry. In future we are going to use it for many other purposes, right? So let's look at or concentrate on this part. By the way, OR is the one which is any input is 1, output is equal to 1, right? AND gate is the one, any input is 0, output is 0, right? And here any input is 0, output is 1. Whereas in this addition, can you logically say something about this addition? Again, sorry, I'm not able. No. Both inputs are same, then output is 0. When both inputs are same or all inputs are same. Let's assume that if it is not like that, if there are three bits are there, let's go this way. Right? So let's look at just some part. Okay, all 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, triple 1, 1. And if you look at the carry, then this is 0, this is 0, this is 0, this is 1, this is 0, this is 1, this is 1, and this is 1, right? So that has to be the addition. Is it fast or going fine? For someone, if it is fast, then let me know. Anybody who thinks this is fast? Okay. we'll revisit that, but this is the gate which is going to be useful for addition. But same way, can somebody tell me how to make subtraction of two numbers, two digital numbers? If I want to subtract them, how to do that? Do we have any logic gate? Do we have any logic gate? So the difficult part of digital is addition is easy, but subtraction is not easy. For subtraction you have to do lots of work. Okay. So this is recorded. This is in recording mode. Okay. Right. So, and I am going to give you these slides also. Okay, at the end. So it's up to you. Concentrate here. Right. So as I was saying, addition is easy, but subtraction is difficult. That's why this is very important topic to learn. Very, very important. Where we are going to study something called the radix complement. So this is the most important topic, and it is used many places. Even at the research point of view, people are doing research in that. And sometimes we are also studying diminished radix complement. Means radix complement is the one, if your base system is 10, then you are finding out 10's complement. By the way, note that what we are studying is for the future subtraction. We want to subtract two numbers. We do not have anything available right now. That's why we are studying this topic, to get the radix complement, so that you can get subtraction between two numbers digitally. I am saying digital things, right? Okay. So let's read this one, which is from same Maurice Mano book. What it says: if there is number is given to you, n, number is n might be anything, 1800 or anything. Let's talk in terms of decimals so that you can understand what we are talking. So n with the base, let's assume that base is also 10. So it's decimal, so it's easy. Having n digits, it might have 5 digits, 6 digits, whatever. Let's say 7932. That's the number. So there are 4 digits in this case. And r minus 1's complement of n. Look at this, r minus 1's complement, not r's complement. R minus 1's complement means, in this case it will be 9's complement. So if I am interested in finding out 9's complement, then this particular complement is known as the diminished radix complement, because the actual radix was 10, but I am subtracting it with 1, minus 1. So that gives 9's complement. Is defined as, so this is the definition, that it's equal to r raised to n minus 1 minus n, where n is the actual number which was given to you. This is radix with whatever the number of digits you have, all of them. Let's assume that in this case, if this is the thing, then 10 raised to 4 minus 1 minus 7932, that is going to be 9's complement. Do you follow, or difficult? Okay. Yeah, at the back, the pink t-shirt. Yeah, you followed or no? Okay. So the technique is, like, before going to all this definition and all, if you want to find out 9's complement, let's say the number is 7932, let's keep everywhere 9. As many number of digits you have, keep those many number of 9 and subtract with that one. That will also give the same answer, right? Because this was 10 raised to 4 minus 1, that's going to give me 49, right? And minus the actual number, right? It's same thing. Either you go with this path or you go with this way. So whatever the complement is required, just keep those numbers over here. If it is 1's complement is required, keep all 1 here, right? But in that case, if let's assume that I have a number 1011, I want to find out, you know, the 1's complement of this one, then let's read this again, where number is n equal to 1011, the base r is equal to 2, r minus 1 becomes ones complement because this was 2. For the complement of 1011, it is diminished radix complement is defined as whatever is written, let us forget about this, keep all of them 1 and subtract with this one, right. This is going to give you the answer, right. So, this is for ones complement. Okay. Easy or no? Just we are reading the definition. Okay. We have not solved any question, but we are reading the definition. So, for decimal number, if base is 10, r minus 1 equal to 9. So, the 9's complement of n is equal to 10 raised to n minus 1 minus capital N. In this case, 10 raised to n represents a number that consists of single 1 followed by all 0, and 10 raised to n minus 1 is a number represented by all 9's. This is what I told. So, for example, n equal to 4. So, it is directly all 9 subtracted, that is going to give you the 9's complement, right. It is very simple, right. Okay. So, this is what the definition wise. Let us go here for the complement of 1011 is just you have to invert whatever the bits are there, just invert them 1 to 0 and 0 to 1, that is one's complement. Okay, before going to all calculation, earlier we were studying the definition, it is general, right, for this one, but this is applicable only for binary system and we want to have one's complement. Okay. So, one's complement is the one where you are going to invert the bit. Yeah, please. Hexadecimal. Okay. Hexadecimal is not the right time to learn now. I will tell you maybe when time progresses, we have the half adder, full adder, other things we will study, right. Okay. Because still people are confusing 2's complement, 1's complement, but this is fine, right. Okay. We will have lots of example, right. We will study that. I am just explaining the things. Okay. So, these are the examples starting with the simple decimal system where you are interested in finding out 9's complement of this number. If I am interested in finding out the 9's complement of this number, it is very easy. Keep all 9, subtracting with the actual number, whatever is coming is 9's complement, and note that this 9's complement, 8's or 10's complement or anything, we are going to use it for somewhere in subtraction in future for our digital subtraction. That is why we are building this theory. Same way, the 9's complement of this one is subtracting all 9 with this number is going to give me the 9's complement. This is fine, right? Okay. Now again, one's complement is too easy, just you have to invert the bit. If you have to find out 1011 000 0101 101, if you want to make the one's complement, it's simple. This become 0, this become 1, this becomes 0, this becomes 0, this become 1, this become 1. Super easy, right? In this case 101 0010. Is it okay? Right? No problem. Okay, now let us make key observation because still we are interested in finding out 2's complement or r's complement. We learn it just for for the intermediate stage, we are going to use it somewhere else. So, what the observation is coming here, the r's complement of n digit number of n in base r is defined as r raised to n minus n, right. For n not equal to 0, if it is 0 then n equal to 0 directly, there is no problem. Comparing with r minus 1's complement, we note that r's complement is obtained by adding 1 to the r minus 1's complement. If you are interested in finding out, let us say 10's complement, then 10's complement is nothing but 9's complement plus 1. 9's complement plus 1. Same way, if I am interested in 2's complement, that is equal to 1's complement plus 1. And I know that 1's complement is super easy, just we have to invert that with something called logical NOT gate, if you know that, right? You know this one, right? This is known as the NOT gate. Some people also call that one as inverter, right? So both are synonyms to each other, right, for digital world. So you can call it NOT gate or inverter, anything is fine. So that will be easier for our case, and just adding plus 1, that will give you 2's complement, right? So this is the definition again. So I am not jumping into that, but that's going to give you the answer. Let's go further. Now I am interested in finding out not the 9's complement, but I am interested in 10's complement with the technique which we learned. So you have to find out 9's complement plus 1. Okay, understand, we are interested in adding, okay, at the end, that's why we are building up. Okay, so we know that 10's complement of this one is 9's complement. 9's complement of this one, what is that, Vidhan? 9's complement of this 2389. Yeah, so 9999 minus this one, so that's going to give me 7610. Adding to 1 is going to give me 10's complement, right? Same way, if this is the case, 0 1 2 3 9 8, you have to subtract all of them with all 9. The number is going to be 987602, right? Sorry, 601, right? And then adding 1 is going to give me the 10's complement, and that's also true for this number also. That's equal to all 9, subtract all 9 with this one is going to give me 9 9 2 3 5 and 7. Adding this with plus 1 is going to give me the 10's complement, right? Let's implement this to maybe further to good number. Okay, okay, yeah. We 7th complement is not defined. We have only r minus 1's complement, right? We are not going to add plus 2, right? Plus 1 is easier, just with 1 bit, last bit. Okay. Okay. So now let's come to the binary system. I want to find out 2's complement of this one. Okay, 2's complement of this one. Answer is already there, but okay. 1011. Okay, what was that? 101100. Let's assume that it's 1. It's like this. I want to find out 2's complement. So first 1's complement plus 1. So what is the 1's complement? You have to invert all the bits 0 1 0 0 1 1 0, and adding this 2 plus 1 is going to give me 1 1 1 0 0 1 0, right? Easy or difficult? Okay, you followed this. This is again a definition. I am following the definition, but for competitive exam people are not following this generally, right? If I want to convert it, I don't follow this. I'll give you the quick trick to find out 2's complement. Okay, it is only for 2's complement, not for 7's, not for 9. Okay, the 2's complement is very important in all digital things. So anywhere you want to go, any competitive exams, 1 or 2 questions will be there from 2's complement, maybe, or even for career and placement you will get it. Okay, so let's look at this. If there is a number like this, okay, you have to start from the right side, right to left. Okay, and you have to find out 1, logic 1. Whenever you are seeing the logic 1, stop yourself there. Let's say in this case it's here. Copy that number as it is, right? And rest of them, whatever is there, rest of them, after this finding out logic 1, you invert all of them. Right? Let's look at the number which we have studied just now. Okay, this number. I am starting from right to left. Okay. Find out where is logic 1. Logic 1 is here. Keep that logic 1 as it is and rest of them invert them. So 1 1 0 0 1 0, right. It's quite fast, right. People are using it for most of the places, right. But the actual definition wise, you have to convert it to logic, you have to convert it to 1's complement and then add it to 1, right. So whichever path you like, you can do that, and if you like the shortcut, this is the shortcut, right. You can reach it here, right. Okay. Can you check this one whether it's working or not? Just make it 1's complement. So 1's complement is equal to 0 1 0 0 1 1 1 0 1. Add that to 1 is going to give me 1 0 1 1 here 1 1 1 0 0 1 0, right. So that's the 2's complement. Okay. So many places you will need that. So let's keep that in our mind, that wherever we want to find out 2's complement, we are going to follow this technique. When we want to have the 1's complement, just we have to invert it, right. So it's all about unsigned numbers. M is positive, N is negative, N is positive. I want to subtract both of them. Then what's going to happen? This is what I want. So if I want to subtract two numbers which are unsigned or the positive in base R, maybe 10 or binary or anything, can be done as follows, right. What you have to do? So that method says that add the minuend M to the R's complement of the subtrahend N, right. So mathematically you are going to do M plus the complement of that one. So that complement is R raised to N minus N, if you remember the definition wise. So that is going to give me M minus N plus R raised to N. So that's subtraction only. So that is going to subtract two quantities and it's fine for me. But here we have to do two things. We have to check which number was bigger. So we have to place sign. It might happen that both were positive. This was like M was less than N, then the answer has to be minus, right. So you have to place the sign whether it's positive or negative. So let's just understand one thing. If there is and carry is available, then you are going to place minus sign before that, right. Let's look at that with some example, then it will be easier. Let's, in this case, I am interested in 10's complement. Using 10's complement, I want to subtract these two numbers. Note that the second number is bigger, so we have to have minus at the end, right. This is what we want. So what our technique says, you just add this M number with 10's complement of whatever the number is, right. Add both of them and look at that whether we got the carry or not. If you get the carry, keep the minus sign. If no carry, no problem. Okay. With minus, okay, one more thing. If carry is there, then the answer is minus and 10's complement of whatever you got. Okay, addition of M plus 10's complement of number. This is what we need to do. Okay. Okay. So if this is the case, let's follow the rule. I know that this is the number. So that number I need first 9's complement. I have to add 2 plus 1. That's going to give me the 10's complement. So that one is pretty easy, right. So that's going to give me this number which is here. You add both the number, we got something, right, and we of course did we got the carry. If sorry, I made a mistake. There is no AND carry. If there is no AND carry, then it has to be minus. Okay. So no AND carry. If there is no carry, then you are going to make the answer is minus of tens complement of whatever the number you got it. So what is the tens complement of this one? Right? Because of decimal it looks pretty long, but for binary it will be easier for my computer. Okay. Okay, any doubt in this? Then we'll proceed for maybe binary number. Do we have now in binary? Look, it's very easy. Using 2's complement, you need to find out the subtraction. You need to find out the subtraction. Look at this: 1 0 1 0 1 0 0. That's x. That is actually m, right? And other one is 1 0. Okay. Can somebody tell me what is the 2's complement of this one? Because that one has to be added, right? 2's complement 0 1 1 1 1 1, sorry, 0 and 1. So this is the one. This is correct, no? Y का 2's complement. It is Y's 2's complement, right? Okay, okay. Look at this. It is second number's complement. Second number's complement, not the first number. Okay. So I was taking the 2's complement of this one. It is pretty fine. Add these two numbers. Tell me if there is any carry or not. If there is no carry, then you have to place minus and you have to take the 2's complement of that one, right? So let's do that. There is a carry, right? So what's going to happen in that case? This is what we got, right? So the answer is as it is. Whatever is coming, just keep that number. That's the answer. If there is no carry, no problem. That's the answer. If there is carry, then add minus and the whole number has to get again 2's complement, right? Okay. Let's take it in reverse way, y minus x. Okay. Instead of x minus y. So just 1 second. 1 0 1 0 0. So this was x and y was 0 4 1 0 1. Okay, 0 4 1 0 1. Right? Let's make it y minus x. Let's make it y minus x. Y minus x. Y minus, okay. In this, y minus x will definitely give you carry because it has to be minus number, right? So y is 0 all 1 0 1. Now tell me somebody wants, what's your name? I forgot. Dev. So Dev, what is the 2's complement here? 0 1 0 1 1 0 0. This is correct, right? Okay. So now add these two numbers. So 1 0 0 1 1 0 1 1 1 1 1. If this is the case where there is no carry, then you have to place minus number and you have to take again 2's complement of this one. So that's going to be equal to, so this will be the answer, right? With minus sign. With minus sign. Process is as follows. So if you want to find out m minus n, then the first number m is going to be added with, let's say for the case of subtraction using 2's complement, right? So then you are going to find out 2's complement of n if there is a carry. if there is a carry, then this rest of the number is the answer, okay, without doing anything. If in case m added with 2's complement of n does not show any carry, no carry. No carry means if m equal to the 7-bit number, n is equal to 7 bits number, so 8th bit is created, is considered as carry. If there is no 8th bit creation, means the whatever the number is coming, you have to add minus sign, and whatever the number you got it, let us say some x number. So, you have to take the 2's complement of x again. Okay. So, that is the technique. New number thing where you have the sign numbers. Just to understand, sign numbers are exactly working as we were seeing them. So, if it is plus 6 and plus 13, I want to see plus 19, that is the answer. Look at this, the first bit is actually 0 0, so it is a positive number. 2 plus 4, it is equal to 16. This makes 8 plus 4 plus 1, 13. So, this is plus 13, this is plus 6, that has to give me plus 19. Let us look at that. So, this addition is 19, 16 plus 3, 19. But now look at the minus 6 plus 13. If it is sign number, if this is plus 1, then 1, 2, 3, 4, 5, 6, 7 and 8, it is equal to minus 2 raised to 8, and rest of the bits you have to add them. Is it making minus 6? Can you check that? Can you check that? What is your name? Yeah. Manaswi, okay. Manushri, okay. So, Manushri, this is fine, minus 6. First number is minus 6 or not? Okay. It is written in book, so it should not make mistake. This is plus 13. So, addition of these two, of course, this is plus 7, right. Same has been checked for different variety of possibilities, right. Okay. Now, there is another number system which is known as the BCD. So, binary coded decimal. By the way, any problem in this one, in sign numbers? Yeah. So, when you are designing your own code or anything, you have to keep uniformity. Answer will be accordingly coming. When you are using K-map and counters, FSM, it will give the same answer. But you have to keep the only one system. You cannot change it. From one is this. Yeah, you have to keep only one system. Correct. Yeah. Check the log. It will give the same answer. Look at this. This is working. This is tried and tested things, right? Okay. So, the next number system is binary coded decimal. So, as the name suggests, right. So, if I want to write down, let us assume that anything from 0 to 9, decimal is actually the one which is written from 0 to 9, right, most of the time, right. Yeah. 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 So, any system in decimal you are writing from 0 to 9, right. So, if it is binary coded decimal, and if I want to write down something from 0 to 9, how you can write down 0 to 9? So, 0 to 9 is as follows. It requires, by the way, 4 bits. What a mistake. Okay. made a mistake. Biometric, okay. It requires 16 combination, right? Okay. Okay, so we want to have the number from 0 to 9 only. So the 0 to 9 is possible from this point to this point, right? Yeah. Yes. In doubt? Okay. So Yash. So 0 to 9, you can write it like this. Now let's assume that I want to write down 19 in binary coded decimal. So you cannot write the way we used to write down in binary system, but what we are going to do, we are going to write 9 separately and 1 separately in binary system. Like 9 is equal to 1001 and 1 equal to 0001. If I want to write down 229, so then I am going to write down 1001, 2 is equal to 01001, right? So it's a binary coded decimal, it's pretty easy. So same thing is followed over here, that decimal BCD digits are going from 0 to 9 and rest of them are going to be rearranged accordingly, right? So let's assume that I want to add two numbers, whether it's giving the same answer or not, right? So you can follow that and you can find out the answers accordingly. I am just skipping this. This is also very simple, right? Okay. So as I have told, there are some numbers 184. Yeah, tell me anything forum? Any problem? Anything? Okay. If I am going fast, then let me know. So what was your adding two numbers?
Making the decimal of 9.
2 to 9. Okay. Okay. So as I already explained, if you want to add two numbers in BCD, like 184 plus 576, so 1 is here, 8 is here, 4 is here, add 5, 7 and 6, add all of them,